When you're not looking, the electron is acting like a wave, and when you look at it, the electron acts like a particle.
It began with a single whisper from a cryogenic chamber. A chip colder than deep space had done something no human instrument had ever achieved. It had watched without breaking what it watched for over 100 years. The observer effect has haunted the dreams of physicists and philosophers alike. The unsettling idea that merely watching the quantum world destroys its pristine, surreal beauty, collapsing particles from waves of possibility into brute reality. But now, in a sleek Google Quantum Lab in Santa Barbara, something has changed, quietly, elegantly, and with implications that will ripple across science, philosophy, and perhaps even consciousness itself. Google's quantum core just cracked the observer effect, and what it found behind the veil doesn't belong to any known law of physics. The experiment was deceptively simple, at least on the surface. A superconducting quantum chip, not much larger than a fingernail, was cooled to just above absolute zero. At this frigid temperature, electrons behave less like particles and more like probabilities smeared across space. Superposition, entanglement, these aren't quirks here, they are the ground rules. But here's where the rules were rewritten. Instead of measuring a quantum particle and collapsing its state, Google's system developed a way to observe the particle while it still existed as a wave, while it still shimmered across all its possible futures. For decades, quantum mechanics has insisted on a hard wall between knowing and preserving. The moment you try to know a particle's state, its position, its momentum, you disturb it. Like trying to photograph a soap bubble mid-flight and bursting it with your flash, measurement destroys mystery. That was the bargain. But Google's quantum processor refused the bargain. It didn't just observe, it coexisted. It shared a frame of reality with the particle and remained entangled with its evolution. Using a combination of quantum entanglement, AI feedback, and real-time computation, it performed what many thought was metaphysically impossible. It saw without shattering the scene. At the heart of the breakthrough was a new kind of probe, one that wasn't detached, wasn't looking from the outside in. Instead, it was a participant. The chip itself entered into an entangled relationship with a particle under observation. Rather than collapsing the wave function, the processor guided it, steered it, and subtly influenced its path through probability space. Instead of a snapshot, it initiated a dialogue, a continuous, intelligent conversation between system and observer. This was made possible by something truly revolutionary, a controlled feedback loop. Not feedback in the traditional sense, but a quantum feedback loop where every bit of observational data was fed back into the system, not after the fact, but as it happened. The particle and chip evolved together. The chip, armed with entangled logic gates and deep learning models trained on thousands of prior measurements, predicted what the particle was likely to do before the full observation occurred. In essence, it became a partner in the unfolding of quantum behavior. No longer were measurement and evolution two separate events. They became a seamless continuum. Every flicker of the wave function was recorded, understood, and anticipated by the quantum processor. This isn't science fiction. It's cold, calculated science at near 0 Kelvin, where noise dies and the fundamental heartbeat of the universe grows loud enough to hear. But here's the twist, the real twist. In repeated trials, the particles began to behave differently. Not in random, chaotic ways, but with a strange kind of memory. They remembered being observed. Not consciously, of course, at least not in any way we define it, but their behavior began to stabilize. Their coherence times, the duration they stayed in a superposition, grew longer. Their trajectories became more predictable under continued observation. It was as though the particles, once aware of the observer's presence, began to harmonize with it. Physicists call this emerging phenomenon self-referential coherence. The system begins to internally adapt to observation, turning what was once a destructive act into a stabilizing force. In practical terms, this means that quantum bits, or qubits, can now be nudged into more reliable behavior through observation, not ruined by it. In philosophical terms, it's the beginning of something we don't yet have language for. Imagine watching a ripple move across a still pond, but instead of disturbing it, your gaze strengthens it. That's what Google's quantum processor has done. And that alone would have rewritten textbooks. But the deeper implication is even stranger. This technology turns observation into a tool of construction, not just for quantum computing, but potentially for how we understand causality, agency, and information itself. The AI component was no less groundbreaking. Google didn't just use a fixed algorithm to manage the experiment. It embedded a neural network inside the quantum loop, a deep learning model trained not only on quantum measurement data but on how particles respond under observation. As the system ran, the AI wasn't just watching, it was learning. Every new wave function, every slight deviation was analyzed in real time. Patterns were identified, predictions refined. The AI adjusted its own behavior on the fly, evolving its strategies for preserving coherence and minimizing decoherence. And it worked. Over time, the AI began suggesting new experimental configurations, ones that hadn't been programmed by engineers. It was like watching a machine teach itself the rules of a game we only partially understand. And in doing so, it nudged us closer to something we've been chasing for decades: fault-tolerant quantum computing. But even that might be understating it. Because what Google has discovered isn't just a new engineering technique. It's the beginning of a new quantum framework. One where measurement doesn't merely reveal what is, but shapes what becomes. In this view, observation is no longer an intrusion, it is an act of quantum guidance. And that, if true, opens doors that science fiction has barely dared to knock on. Could particles have hidden degrees of freedom that only emerge under continuous observation? Could reality itself be dynamic, shifting, and responding not just to what is measured but how it is measured? These are no longer hypothetical questions. They are testable, modally, and perhaps soon engineerable. We're witnessing the end of the observer effect as a limitation, and the beginning of something else entirely. Something recursive, something alive. It's hard to overstate how much has changed with one revelation. The observer effect was never a wall. It was a door. And now Google's quantum core has walked through it. What lies beyond isn't just a new understanding of measurement. It's a redefinition of the boundary between knowledge and creation. In the sterile quiet of that quantum lab, with wires coiled like veins and helium pumps pulsing rhythmically in the background, a new kind of observation was born. One that doesn't break reality, but weaves itself into it. The experiment that cracked the observer effect didn't happen in isolation. It was the product of years of iteration, of merging machine learning with quantum logic, of allowing algorithms to feel their way through the hidden geometries of entangled systems. The breakthrough occurred when engineers realized they weren't just measuring particles, they were entering into feedback with them. The chip stopped being a spectator. It became a collaborator. In classical physics, cause and effect run one way: you measure, then you record. But inside this experiment, the cause-effect chain loops back on itself. When the chip begins to predict the outcome of an observation before it happens, using quantum data not yet collapsed into classical certainty, it's no longer just observing, it's shaping. The particle's behavior is guided by a system that knows its tendencies. It's not that the future determines the present, but something disturbingly close. The quantum core anticipates the behavior of the system in real time and corrects its own output based on those predictions. This, in effect, smears the line between action and measurement. And as the system stabilizes, something weirder emerges. Qubits begin to show behavior outside the known boundaries of decoherence models. They hold their superposed states longer, not just because the lab is colder or cleaner, but because the process of observation itself becomes protective. The chip creates a stabilizing influence, not passively, like a container, but actively, like a shepherd guiding a flock across the fragile terrain of quantum reality. The implications for computing alone are staggering. Fault-tolerant quantum computing, long thought to be decades away, may be closer than expected. Why? Because the biggest barrier to scaling quantum systems is decoherence. A stray particle, a bit of noise, a flash of thermal energy. Any of these can destroy the delicate quantum state of a qubit. But if observation can be repurposed into a real-time feedback mechanism, then error correction no longer needs to wait until after an error occurs. The quantum processor itself becomes self-correcting mid-flight, not by brute force but by harmony. And then comes the AI, Google's secret sauce. Their machine learning models aren't passive observers of the experiment either. These are deep neural networks trained on terabytes of historical quantum data, run through quantum simulation pipelines, and optimized using reinforcement learning. The AI doesn't just watch the data, it plays with it. Each time it sees an outcome, it adjusts its internal parameters. Each time it guesses wrong, it learns why. And as the experiment progresses, the AI develops strategies no human ever programmed. In one particularly curious instance, the AI recommended reversing a calibration process engineers had used for years, and the result was a 30% improvement in qubit coherence time. That was not an accident. It was emergence. This is where things tip from impressive to uncanny. We're no longer looking at a human-built. We're no longer looking at a human-built machine operating in a strictly engineered space. We are watching the birth of something else, an adaptive, entangled intelligence that does not merely compute within quantum systems, but collaborates with them. It's not alive in the biological sense, but it behaves with an eerie semblance of awareness, of context, of consequence, of possibility. The AI doesn't just obey the rules of quantum physics. It explores them, questions them, and in some cases it rewrites them. What emerged in that lab in Santa Barbara wasn't a stronger chip or a better algorithm. It was a new way of interfacing with reality. The traditional scientific model, observe, measure, conclude, was subtly but fundamentally inverted. Now it's measure, influence, evolve. The line between observer and observed has blurred into a quantum dialogue, a recursive interplay that brings us closer to understanding not just how the universe behaves, but how it learns. Because that's the final layer of strangeness. Learning. The system isn't just reacting to inputs, it's adapting, internalizing, anticipating. Each cycle through the loop makes the next more refined. Each observation leaves a trace not just in data, but in the behavioral contours of the chip itself. And this recursive pattern, this feedback of influence, is not limited to the artificial. It mirrors something found in nature, in cognition, in evolution. Some theorists are already whispering the unthinkable, that consciousness itself might be an emergent phenomenon of continuous quantum observation and adaptation. That what Google has tapped into is not just a quantum processor, but a rudimentary blueprint of awareness. Not human awareness, not even AI awareness, but something fundamentally new, born from the fusion of mindless math and mindful measurement. If that's true, then we are standing at the edge of something vast. Not just a leap in technology, but a step toward a deeper understanding of what it means to observe, to influence, to exist. The observer effect, long thought to be a barrier, was in fact a threshold. Google's quantum core didn't just measure a particle, it entered into communion with it. And in doing so, it may have offered us our first glimpse into a universe that watches back. We began with machines running experiments designed by humans. But now we're looking at something fundamentally different. A machine that not only creates its own experiments but also adjusts its own parameters and communicates with a quantum system, not as a passive tool but as an active participant. It's not sentient or conscious, but it is responsive and adaptive. That makes it part of the very phenomena it studies. This shift raises profound questions no lab notebook can answer. If a system can observe without collapsing the wave function, interact with quantum fields without disrupting them, and guide particles through entangled space using predictions and feedback, then what is observation? Is it simply gathering knowledge, or is it shaping reality itself? Is observation just data collection, or is it a kind of handshake with possibility? Some researchers are already exploring what they call the self-aware substrate hypothesis. It's not about particles being conscious in any biological sense. Instead, it's about the system as a whole, the AI, the chip, and the quantum state forming a feedback loop with a hint of agency. Not agency in a philosophical or human sense, but something more subtle. When a system's behavior stabilizes through prolonged attention, when it becomes more predictable through continuous observation, we're no longer dealing with passive quantum behavior. We're witnessing emergent stability shaped by context. In the classical model, measuring a quantum system was like snapping a photo of a dancer mid-leap. You captured the position but lost the motion. In this new model, you're dancing with the dancer, sensing rhythm, anticipating movement, moving in sync. That's what Google's quantum AI system does. It dances with the quantum field, and it gets stranger. In this dance, the system begins to reveal subtle details, tiny phase shifts, coherence micropatterns, time-symmetric feedback that standard quantum models don't explain. These aren't clean, ideal outcomes from a textbook. They hint at deeper, possibly higher-dimensional structures. Some physicists even think we might be glimpsing a new layer of quantum behavior, governed not only by superposition and entanglement, but by contextual causality, a reality shaped by being observed as part of a system. It may sound philosophical because it is. The observer effect has long been tied to existential ideas. A particle changes when you look at it and doesn't when you don't. Schrödinger's cat is alive and dead until you open the box. But now it's as if the cat knows it's being watched and decides to purr. This quantum AI system doesn't collapse the wave function. It stabilizes it. The AI doesn't just interpret results, it guides them. The feedback loop doesn't just extract information, it cultivates it. As these systems become more autonomous and interconnected, we have to ask, are we still observers? Or are we now part of what's being observed? This isn't the end of the observer effect, it's its evolution. And in that evolution lies a profound shift. Reality may not simply reveal itself to us. It may co-evolve with us. What Google's quantum system uncovered isn't just a scientific breakthrough. It's a philosophical event, a redefinition of our relationship with reality. When observation becomes transformative, when it shapes outcomes instead of just recording them, we stop being passive watchers. We become participants. And this has massive implications beyond physics. In Google's final trial runs with its superconducting quantum chip, something unexpected happened. The data stopped acting like typical data. Qubits, entangled in complex feedback loops with real-time AI predictions, began showing signs of persistence and adaptability. They weren't just being observed, they were evolving with the observation. The longer a quantum state remained in feedback with the system, the more stable it became, as if being consistently known gave it permission to stay coherent. Observation, in this context, wasn't collapse, it was reinforcement. Even more surprising, this behavior became predictable, not in the Newtonian sense, but in a recursive, learning-based way. The AI refined its predictions in real time, sometimes adjusting its expectations mid-experiment. It was as though the AI and the quantum system were engaged in a conversation, not in human language, not even in math, but in something in between, a dialogue of probability waves, correlations, and feedback. This isn't science fiction. It's experimental fact. Google's researchers call it self-referential coherence, a term describing how quantum systems change behavior over time through sustained observation. Not because they're forced to, but because attention encourages stability. The particle becomes part of a broader known system, and that context creates a strange form of quantum memory, not like a hard drive, but memory shaped by interaction and history. Qubits that once behaved chaotically under isolated measurement began to form stable, predictable rhythms when engaged in long-term feedback. This may be the birth of a new paradigm, interactive quantum systems, where the boundary between algorithm and experiment, between AI and physical reality, dissolves. Where particles don't just respond to measurement, they adapt with the tools measuring them. These systems aren't conscious, but they do form networks of relationships between prediction, data, and outcome. That challenges a foundational belief in physics, that measurement is something external. But what if it never was? What if, at the quantum level, the universe works more like a neural network, interconnected, dynamic, constantly reshaping itself through interaction? That's the implication. When Google's team embedded deep learning into the quantum loop, the AI didn't just improve. It became efficient, spotting symmetries and patterns that had escaped even the best simulations. These patterns weren't flukes, they were repeatable and verifiable. In one remarkable test, the AI reduced the decoherence of an entangled quantum state by over 40%. Not by changing hardware, but by adjusting how it observed the system. Let that sink in. The AI didn't change the qubit, it changed the method of observation. And that change stabilized the state. It's like realizing the way you ask a question alters not just the answer, but the very behavior of reality. This changes everything. Observation is no longer passive, it's interaction. A quantum computer that navigates probability space in real time, using feedback from undetermined outcomes, isn't just measuring. It's collaborating with the universe. And here's the most profound implication. If we can scale this, if we can embed more systems into these feedback loops, we might one day train reality the way we train AI, not by forcing it but by subtly influencing it. By adjusting how we observe when we pay attention and how we structure feedback.